So, let us look at one more example. The other example that I have, example number 10. So, this is a problem in 2D, and the problem says that we have to look at the motion of a particle in a plane. So, this is a problem in 2D. Plane under a central force, under a central force whose potential, under a central force whose potential per unit mass, potential per unit mass is V, with the Hamiltonian given by h of q bar comma p bar, given by 1 by 2 of p1 square plus p2 by q1 whole square plus v of q1, right. So, suppose the 2D problem would have been in the polar setup. Suppose we were describing the problem in polar coordinates, then people can recognize my coordinate q1 as my radial coordinate. So, just a trivia, in polar form my coordinate q1 is r, which is the translational variable, and my coordinate q2, which is theta, is the rotational variable, right. Okay. So, let us move ahead. So, from here I can write down my solution to the reduced Hamilton-Jacobi equation. I see that this is also equal to, I replace my pi's to be del psi del qi's. So, my equation looks like following. So, 1 by 2 del psi del q1 square plus 1 by q1 square times del psi del q2 whole square plus v of q1, this is equal to E. From here I can multiply throughout by q1. So, I get an alternate form, q1 square times del psi del q1 whole square plus 2 times v of q1 minus E, right, plus del psi del q2 whole square, this is equal to 0. The reason for writing it in this form is, notice that this is purely a function of q1, while this quantity is purely a function of q2, and that will help us to select our quantities g1 and g2. So, let me select our, in the solution strategy, let me select our g of q1 comma del psi del q1, the function, to be q1 square times del psi del q1 whole square plus 2 times v of q1 minus E, right, and my g2 is g2 of variable q2 comma del psi del q2 is equal to del psi del q2, right. So, what we do is we seek solutions of the form psi is equal to psi 1 plus psi 2, right. So, psi 1 is a function of q1 comma alpha. So, alpha comes out to be typically these are constants or the functions of capital Q, which is the generalized coordinate, right, and psi 2 is psi 2 of q comma alpha. Okay. Well, q, not q but q2. So, this is q1 and this is q2. So, then let us so where my alphas, so alpha bar is alpha 1, alpha 2, these are my constant vectors. So, these are my constants. Okay. So, what we do is we take we within this constant we are going to take one constant alpha 1 to be 2e, right, because we have a 2e which is appearing in this setup. So now the next stage involves the solution of ODEs that we have. G is equal to Ci's. I see that let us set up the ODEs. The second ODE is quite easy to set up. So del psi del q2 is equal to alpha 2, or I see that psi of q2, so this is, so the corresponding ODEs are G1 is equal to alpha 1 and G2 is equal to alpha 2. These are my ODEs, right. So this is equal to alpha 2 q2, and why we have avoided the constant of integration, because we want to express our final answer in terms of only two constants, alpha 1 and alpha 2, right. 2D problem, two constants. So psi of q2 is as follows, and then also for the first case we have q1 square del psi del q1 whole square plus 2v of q1. I am just writing this expression here, minus alpha 1, right, plus so this is also equal to plus alpha 2 square is equal to 0, right. Okay. So yeah, where did this happen? Because we have in our original, this is plus alpha 2 square because of the Hamilton-Jacobi equation. This is, let me call the Hamilton-Jacobi equation as star. So this is from star, right. So now I have to solve for psi 1. So these are my this is my equation for psi 1 as a function of alpha 1 and alpha 2. So I can directly, let me write down the expression directly. So psi 1 of q1 comma alpha comes out to be the integral of square root of alpha bar, alpha integral of alpha 1 minus 2v of q1 minus alpha 2 square by q1 square, right. Let me call this quantity as square root f dq1, right. And so I leave the solution in this form, where f is a quantity inside this integral, assuming that so f is in general, so this is square root of f of q1 comma alpha bar, assuming that this can be integrated. So then all I do is I check whether the solution is complete or not. So check this matrix del 2 psi del qj del alpha k. I see that this is a 2D matrix, 2 by square root f minus alpha 2 by q1 square root f 0 1, and I can see that the determinant of this is equal to the determinant of this matrix, which will be 1 by 2 square root f. This is not going to be 0, provided my function f is well defined or positive. Okay, provided if my f, the function, is positive, right. Okay. So then in that case I can directly write down my Hamilton's equation. My Hamilton's equation to give me the extremals are as follows. So beta 1, this is for the original setup, which involves time, right. So my beta 1 is negative del psi del alpha 1 minus t. I just plug in the value of psi. So that will be, after plugging the value of psi, I get that this is negative half. This is still left in the form of the integral square root of f minus t, and beta 2 is negative del psi del alpha 2, right. And then again I keep it in the form of the integral. So this is integral of dq1 by q1 square root f minus q2, right, where my beta k's are constants. My beta k's are constants, and note that my P2, so my beta k's are constant. Note that, so that is the end of the problem. The problem, final step of the problem involves inverting these two relations to find my Q1 and Q2, which is my extremal to the Hamiltonian system, right. So note one thing, note that P2, the second component of the momentum, or the second component is del psi del q2, right, but this is, notice that del psi del q2, del psi del q2 is a constant, right, by the setup of our problem. This is also equal to alpha 2, which is a constant, which means, now notice that to begin with, in polar coordinates we had assumed that the second component involved represented the angle or the rotational component. So P2 is the angular momentum in the physical language, and we are showing here that in this setup the angular momentum is constant. So this statement, so this is nothing but our angular momentum, or the rate of change, or or the change in the angular component of our solution, and we are saying that the angular momentum is constant, meaning that we are saying that the law of conservation of angular momentum is satisfied in this problem. So conservation of angular momentum is satisfied in this problem. Okay. So let us now consider. So far we have shown that if we are able to separate variables for conservative system, we should be able to solve and find the generating function, which will give us the extremal to the original functional. The question is, can we really separate out the separate the variables? Now I am going to state some conditions under which the reduced Hamilton-Jacobi can be variable separated. So conditions for separation of variables, for separation of variables, right. So it turns out I am going to write some criterias which is true, and I am going to state some results in the form of theorem without proof. So separation of variables for Hamiltonian system, separation of variable for Hamiltonian system may not exist. There is no guarantee, which means that no guarantee that GKs can be found. There is no guarantee that GKs can be found, and it turns out that we will see that a coordinate transformation can affect the process, right, which means that in one coordinate the separation of variable can be done, while in another, for the same problem in another coordinate, that it cannot be done. We will see some examples. Also, it turns out that the necessary and the sufficient condition for separation of variables of Hamiltonian system with, there are three results that I am going to state for different coordinate systems. So with orthogonal coordinates. So what do I mean by orthogonal coordinate system? That is system in which no product terms q k dot q j dot involved in our Hamiltonian H, right. So those are my orthogonal coordinate system. It turns out that there is a necessary and sufficient condition given by Liouville. I am going to state these results. Liouville for n is equal to 2 and by Steckel, the German mathematician Steckel, for n greater than equal to 3, right? And finally for by Levi-Civita for non-orthogonal systems in general, right? So we have the condition for all the cases, right? Okay. So let us now look at these. I am going to end my discussion by stating all these results, few of these results. We consider our Hamilton-Jacobi equation of the form that we have seen in our separation of variable. So let us say we have the following form, which is half k from 1 to n ck of del psi del q k square plus the function v is equal to alpha 1, right, where alphas are constants. Okay. So let me call this as our expression 1, right. So the first result by Liouville, so this is my theorem number 17, this is the theorem by Liouville, or the result by Liouville. This is for two-dimensional problem. It says that a necessary and a sufficient condition for the Hamilton-Jacobi equation, half C1 times del psi del Q1 square plus C2 times del psi del Q2 square plus V of Q bar is equal to alpha 1. So this is a problem in 2D. So this is n equal to 2. So a necessary sufficient condition for this equation where my constant ck's are positive functions of my variable q bar, to have separable solutions is the existence of these constants nu1 mu1 sigma 1 and nu2 mu2 sigma 2. So the existence of these two pairs of constants, depending, these constants, they all depend, well, these are not constants but these are functions. So depending on q1 and q2 respectively. So the first pair depends on q1 and the second set of functions, they depend on q2, right, such that my function v, this function v here, so v can be written as nu1 plus nu2 divided by sigma 1 plus sigma 2, and c1 is mu1 divided by sigma 1 plus sigma 2, and c2 is mu2 divided by sigma 1 plus sigma 2. The moment we are able to write these these functions of the generalized coordinates capital Q and this function v in this form, then we are guaranteed to have a separable solution. That is what Liouville stated and proved, right. And then let us look at an example. The example that I have in mind is the example that we just considered of the central force problem, example number 10, few slides back. So the problem is this one. So I am going to reconsider my problem, this one, this one, right. So this is the problem which is example number 10 here, right. Okay. So recall example 10 that was done few minutes back. See that my Hamiltonian leads to the following Hamilton-Jacobi equation, which is times q1 square del psi del q1 whole square plus del psi del q2 whole square plus plus q1 square v of q1 by q1 square. So this is how I am writing the equation. This is equal to alpha 1, and that can be put in the Liouville's form, This can be put in the Liouville's form if I take my mu1 to be q1 square, I take my mu2 to be 1, I take my sigma 1 to be q1 square, I take my sigma 2 to be 0, I take my nu 1 to be q1 square v of q1, and I take my nu 2 to be 0. The moment we take all these quantities as follows, we will see that this equation reduces to the Liouville's form as specified by the result in theorem 17. Okay. So that is the end of this discussion, but let us also reconsider this problem. So reconsider this problem, example 10 in Cartesian form, right. So in Cartesian form, notice what is happening in the Cartesian form. My Hamiltonian h of x comma y, right, now can be written in the following. So 1 by 2 del psi del x whole square plus del psi del y whole square plus v of q1. So v is a function of q1, but q1 is r, but r is in Cartesian form x square plus y square under the root is equal to alpha 1. Notice that the central force v1 here depends on the square root of the function x square plus y square. So in this case we cannot separate v1, we cannot separate the variable x and y in this function as such, unless and until this function itself is a constant, or in other words, this function cannot be written in the Liouville's form, or we cannot use the separation of variable when the same Hamiltonian is written in the Cartesian form. So the moral of the story here is that the transformation process from one coordinate frame to the other may affect the solution methodology. So finally, let me write down this statement. So what I said is the following in this example. So we cannot get V separated, as required by Liouville's theorem unless V is equal to a constant, right. So which means no separable solution exists for the same problem in Cartesian coordinates, right, for the same problem. However, in polar we saw that a solution exists, separable solution exists. So I end my discussion here due to the lack of time, but we are going to continue and finish our discussion on the results of how can we separate solutions for higher dimensions and also for non-orthogonal coordinate. But more importantly, we are going to look at a very, very important result by Noether, which gives the relation between finding the conservation laws and the so-called transformations, which reduces our functional, the function or the integrand in the functional. So thank you very much for listening. Thanks a lot.